After watching this video, you should be able to provide a basic explanation using the particulate model of matter to describe why the temperature of a liquid, for example, remains constant as it boils. I want to start off by looking at a plot of energy as a function of temperature for the heating of a liquid. And let's imagine, for example, we started to heat a liquid up below its boiling point. We know that the temperature would slowly increase as energy is put in. And now, once we get to the actual boiling point of the liquid, additional input of energy does not cause the temperature to go up. And this is at the point where the liquid is actually boiling. And this occurs until the liquid has completely boiled, and once it is completely in the gas phase, additional input of energy will again raise the temperature up. So the question is, how can we use the particulate model of matter to describe what's going on right here in this plot? Alright, to illustrate this, I want to pull up the molecular dynamics simulation that I've been using in class. And here I'm trying to simulate what a liquid might look like on the particulate level. And I have these liquid particles moving around. And you can see that there's a distribution of kinetic energy of these particles. Some are moving a little bit faster, some are moving a little bit slower. If there's one that's moving faster and is near the surface, there's a probability it can escape, like some of these are, up into the vapor phase, which sets up the vapor pressure of the liquid. And now we know that if I increase the temperature slightly here, that the average kinetic energy will increase. So I'll just pull the temperature up, and you can see the average kinetic energy goes up. And you can also see that there are more of the liquid molecules that can actually escape into the vapor phase. So as we heat a liquid up, the average kinetic energy would go up, and so would the vapor pressure of the liquid. Now, when we get to the boiling point temperature of the liquid, at that point, any additional energy that we put into the system does not go into increasing the average kinetic energy of the molecules, but actually goes into pulling the particles apart, increasing the potential energy of the system. So I'll kind of try to simulate that. Imagine I get to the phase change temperature, and now the energy I put in now goes in simply to pulling all the particles apart, increasing the average potential energy. And now throughout the phase change process, the average kinetic energy stays the same, and as you can see here, I pretty much boiled this liquid. And now if I add additional energy from this point on, once it's all in the vapor phase, the average kinetic energy will once again begin to increase. Alright, let me explain this concept of potential energy a little bit more as it applies to the phase change of a substance. If I draw a plot here, similar to the one we have in the notes, that plots potential energy as a function of the distance between two particles, we could see that at very long distances, the potential energy between two particles that have an attractive force between each other is small and close to zero. And in fact, we by convention define the potential energy equal to zero at this point in the line when these two particles are infinitely separated apart. But as they approach each other, the potential energy starts to become slightly negative. And the value of that negative number is a function of the distance between the two. So as the particles get even closer together, we can see that the potential energy becomes even more negative. And they get closer, it becomes even more negative. If these particles get too close, because there's a repulsive force between them, the potential energy can actually shoot back up again of the system. If they get too close, there is a potential for them to push away from each other. So we can see that potential energy is a function of distance between two particles that are attracted or have a repulsive force. So when a liquid is undergoing a phase change to a gas, we say that all of the energy that we are putting in at the phase change temperature is being used to increase the potential energy of the system. The energy is being used to pull the particles apart from each other, but not to increase their average kinetic energy. Therefore, on a macroscopic scale, we observe that the temperature remains constant throughout the phase change process. If we're, for example, condensing a liquid, then all of the energy extracted out allows for the particles to get closer together. And throughout that energy extraction, the average kinetic energy remains constant, and the temperature also will remain constant. So in our phase change, we observe that the temperature, or what we refer to as the average kinetic energy, remains constant throughout the process because all of the energy is being either put in or taken out in the form of potential energy.